get started. So welcome to the keynote, second keynote of the program. Is to conclude today's exciting, days of talks, and it's my pleasure to introduce Professor Edward Lee from the University of California at Berkeley. And he's so well known that really needs, no introduction, but I will. But I'm going to only highlight some key facts about Professor Lee, because otherwise I may have to fill up the entire hour and he has no time to give his speech. So Professor Lee has been working on cyber physical systems and embedded software systems for 40 years. After studying and working at Yale, MIT, and Bell Labs, he landed at Berkeley, UC Berkeley, where he is now professor of the graduate school in electrical engineering and computer science. His research is focused on cyber physical systems. He is the lead author of the open source software system, Dynamite 2, or the second, author of textbooks on embedded systems and digital communications, and has recently been writing books on philosophical and social implications of technology. His current research is focused on a polyglot coordination language for distributed real-time systems called Lingua franca that combines features of discrete event modeling, synchronous languages, and actors. Without further ado, let's welcome Professor Edward Lee for his keynote.
Thank you, Albert. That was a very nice introduction. It's a real honor to have been invited to give this talk. Let me share my screen and start up the presentation. So I'm going to be talking today about an obsession of mine that I've actually had for quite a long time. And I wanted to just start by offering some pointers in case the topic intrigues you and you'd like to look some more. The shortest one is a recently published blog, which is really kind of a really short synopsis, almost a position statement on the SIGBED blog. There's also a very recent paper that just appeared last month in the ACM Transactions on Embedded Computing Systems on determinism. But I've also written 4 books that touch on this subject from various perspectives. The Ptolemy book is all about modeling and design of concurrent and real-time systems. And it has a very heavy emphasis on deterministic approaches to design. The Introduction to Embedded Systems book is it's a quite technical textbook that has a very strong focus on modeling, and it talks both about the use of deterministic models and also the use of non-deterministic models. And then these other 2 books are really much more philosophical. The Plato and the Nerd book has an entire chapter on determinism. And the Coevolution has a few discussions, some of which I will be highlighting in this talk. So as you can see from this, I've really been thinking about this topic for quite some time. And even though I've been thinking about it for quite some time, it's still, even with all that effort that I've put in over the years, a topic that's really rather difficult to get one's head around. And especially if you approach it from the foundations in physics and philosophy, where a common definition that you'll find is that determinism is the principle that every action is a consequence of preconditions and a set of fixed rules that then govern how those preconditions lead to some other external conditions. But this is not, whoops, hold on one second. This definition is really hard to work with. And one of the concepts that's very integrally tied with this definition is the notion of causation. There's this idea that preconditions cause the consequences. And this binding of the notion of determinism to causation, I think, is one of the reasons for a very strong and prevalent distaste for non-determinism in models of the physical world. People, I think, have worked for centuries to try to banish non-determinism from models of the physical world. And I think it follows from distaste for uncaused action. And that distaste, I think, is really quite profound in humans. And we even, invent God, for example, to ensure that there always is ultimately a cause for any action. So this distaste is really quite profound. But the notion of causation really doesn't have to be tied that tightly to the notion of determinism. And in fact, the notion of causation is itself actually sort of problematic. Bertrand Russell, way back in 1913, was kind of famous for challenging the scientific community, saying that causation is actually not a foundational property of models of the physical world. In this very colorful quote, he says, "All philosophers of every school imagine causation is one of the fundamental axioms or postulates of science. And yet, oddly enough, in advanced sciences such as gravitational astronomy, the word cause never occurs. The laws of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone era, surviving like the monarchy only because it is erroneously supposed to do no harm." So this notion of causation, in fact, some psychologists believe that it's actually a result of evolution, that that the very strong notion of causation that humans have is a consequence of its survival value and not a consequence of some fundamental principle of the physical world. So this binding leads to really profound difficulties with getting a handle on this notion of determinism from a scientific or philosophical perspective. So there's this wonderful book by John Earman, A Primer on Determinism, that looks at the problem from many different angles. And right in the preface, Earman gives up and says, this is already enough to make a strong suspicion that a real understanding of determinism cannot be achieved without simultaneously constructing a comprehensive philosophy of science. And then he says, I don't have such a philosophy, and so I have to approach this with humility and cowardice. So this notion from this philosophical side is rather difficult. So we can make it a lot simpler, however, if we approach it from more of an engineering perspective. So determinism is really about resolution of alternatives. When it's possible for more than one thing to happen, when, how, and why is one chosen over another? How do the alternatives get resolved? Why do they get resolved? And when do they get resolved? These three questions, when, how, and why, are actually three different questions. And you can approach the problem from the perspective of each of these. So let's try focusing on just when. So when are alternatives resolved? And I'm going to borrow some content from my most recent, more philosophical book. This one was published just last year in the middle of the pandemic. So there was no book tour, there was no nothing. It didn't really get much attention. But one of the things that it approaches is this question of determinism, and it's actually approaching it from the perspective of trying to get a handle on the question of whether AIs will ever be able to acquire free will. You can imagine that's probably a pretty difficult question to answer. But free will is another concept that is very tightly tied with this notion of determinism. And in this book, I suggest focusing on the question of when alternatives are resolved. And in chapter 12 of this book, I go through an exercise of constructing models of what I think are the simplest possible universes that have the possibility of free will or no free will. Okay, that's an exercise that I go through, and I construct these automata, and I use automata theory to analyze it. So here's an automaton that represents what the physical world might look like in the simplest reduction of a physical universe if the universe is actually deterministic. So in this model, there's a little bang, not a big bang because it's a really small universe, and a being comes into existence, and that being can only do one thing. Well, there's two alternatives, but in its life, it only does one thing. It either ticks or it talks. Okay, so after the little bang, in a deterministic universe, it's already preordained. If it comes into existence along this upper path, it's going to tick. If it comes into existence along the lower path, it's going to talk. So this is a model of what the physical world might look like if everything is preordained as of the Big Bang, okay? A non-deterministic version of that has the being come into existence at the little bang, and then the being still has the possibility of ticking or talking. So if you look carefully at these two automata, you see that the essential difference is when the resolution of alternatives occurs. In the deterministic universe, it occurs early. In the non-deterministic universe, it occurs late. And that's really the only difference between these two automata. So now the question becomes, what can we say about our ability to distinguish these two automata? And in this book, I use the theory of automata that was largely developed by Robin Milner, and in particular, his notion of bisimulation relations between automata. And I prove that it's impossible to tell objectively by observation alone which of these two scenarios you have. You can't tell when the resolution of alternatives occurred by just observing. And this is very carefully constructed in the book because I have to make sure that the observer is actually part of this tiny universe. So the tiny universe has to become a little bit bigger. The observer becomes an automaton. The relation between the observer and the observed is a simulation relation. And I show, using the concept of bisimulation, that it's impossible to tell the difference between this deterministic world and this non-deterministic world by observation alone. However, you can tell the difference if you can interact. If the observer can interact with the being, then it becomes a subjective first-person kind of interaction. And in that case, it becomes possible to tell the difference, but not up to 100% confidence. I show that, in fact, you can build an arbitrary amount of confidence as close as you like to 100%, but you can never really actually get to 100%. So this suggests, I think, that there's a tremendous amount of subtlety in this question about determinism in the physical world. And this impossibility result may say, okay, really, we're never going to be able to resolve that question. But there's a much simpler question that we can resolve. And that question is kind of evident when you look at these two models. Just looking at these two models, you can see there's a very big difference between them. And in fact, if I focus on the behavior of the beings after they come into existence, automata theory tells me very simply that this upper circled sub-automaton is deterministic, and the lower one is non-deterministic. And there's a very clear distinction between these two. If I focus on the model, the difference is obvious. So my suggestion is that it makes much more sense to approach determinism as a property of models. And once you approach it as a property of models, it becomes a much simpler concept. So, and it's easy to define as well. So a model is deterministic if given some initial state and some set of inputs, the model defines exactly one behavior. Now, I've highlighted in italics and in red 3 words here, all of which you have to define before this definition of determinism is complete. You have to define what you mean by the state of the system, the state of the model. You have to define what you mean by the inputs, and you have to define what you mean by behavior. But once you've defined these things and created a formalism around that, which is something that we do all the time when we construct models, then the distinction between deterministic and non-deterministic models becomes really quite straightforward. So given that definition, you can recognize that, in fact, deterministic models have proved incredibly valuable in engineering enterprises. single-threaded imperative programs are, in fact, deterministic models. What are they modeling? Well, ultimately, they're modeling the sloshing of electrons in an underlying computational fabric, right? The physical system is just electrons sloshing around in silicon, but the model itself is deterministic, as long as you're careful to define behavior. So for example, if I take as a model a C program, and if I include as the behavior the timing of that program, then it's not a deterministic model. But if I include as behavior only the bit transformations that the program does, then it is a deterministic model. So depending on how I define behavior, I either get a deterministic model or a non-deterministic model. But the determinism of a single-threaded imperative program, when you've defined the inputs and the behavior correctly, has proved to be an incredibly valuable property. In fact, I would argue that there's no way we would be doing the world's finances on computers if it weren't for the determinism of the single-threaded imperative program model. And of course, the determinism of that model depends on other underlying deterministic models as well. Instruction set architectures, we go to great lengths to build those as deterministic models. Synchronous digital logic, which is what we use to realize these instruction set architectures. These are deterministic models as well. And the determinism of these models is exceedingly valuable. Let's zero in for a minute on really what is the value of deterministic models. Well, one of the key properties of deterministic models is repeatability. You give the model the same inputs, you get the same behavior. That's the foundation of test-driven design. It's what enables us to do regression tests on software. If you don't have determinism, it's much more difficult to do testing. So some of you may remember the various incidents of unintended acceleration in Toyota vehicles, and NASA was contracted by the Department of Transportation, the US Department of Transportation, to study the problem. And NASA's study came to the conclusion that the Toyota software was untestable. And it was fundamentally because the software was written in a highly non-deterministic way. And so regression tests and the usual sort of test-driven design techniques simply don't work for that kind of software. So this property of repeatability is a consequence of using a deterministic model. Another valuable property of deterministic models is it's easier to build consensus. So for example, your bank comes to the same conclusion about your bank balance as you do when you balance your checkbook. Well, does anybody balance their checkbook anymore? I do, but I guess I'm a little old-fashioned. But in any case, the issue there is that there's a deterministic model behind what the banking system is doing for us. And as a consequence, even though we carry out the algorithms in different ways, because it's a deterministic model, independent agents will agree on what the results should be. That's also an extremely valuable property. Now, predictability is a property that is often associated with deterministic models. And in fact, some deterministic models are predictable, but a lot of them are not. And let me cite a really nice piece of work that really underscores the fact that determinism does not even in principle imply predictability. So this is a study done by Lewis and McGregor, published in 2006, where they proposed a thought experiment. And this thought experiment was just a physical system with two spheres colliding. And they constructed a model of it. So we can look at the determinism of this model, okay? We don't have to go to the physical world. We can just look at the determinism of the model. Then they asked the question about to what precision do they need to know the initial conditions of the system in order to be able to predict the behavior after a certain number of collisions. They determined that to be able to predict behavior after just 35 collisions, if they were to measure the initial positions of these spheres optically, then they would need to use an optical technique of such a small wavelength that a single photon of such light would have more energy than is posited for the entire universe. One photon. That's the level of precision with which you would need to be able to know the initial conditions in order to be able to predict behavior after 35 collisions. This is an example of a very common class of systems that are referred to as chaotic systems. So Edward Lorenz was a meteorology professor at MIT who was a pioneer in the 1950s and 60s of doing computer modeling of weather. And it was incredibly frustrating to Lorenz that these models, even though they were really quite sophisticated thermodynamic models of weather, were unable to predict weather accurately more than a few days in advance. And he identified that the problem was not in the models, nor in the techniques that were being used to solve the models on the computer, but that this was actually a fundamental property of the thermodynamics, that the systems were chaotic, meaning that arbitrarily small perturbations in the initial conditions or arbitrarily small errors at any step of the way would have arbitrarily large consequences in the future. So Lothar Thiele and his group at ETH showed that chaos arises in real-time scheduling. There's this wonderful paper from EMSOF 2015, and this plot from this paper that shows response time across jobs and shows distinctly chaotic behavior. It's impossible to predict behavior into the future, given really quite a simple model of the real-time scheduling problem in this particular case. So determinism doesn't always come with predictability, but some deterministic models are predictable. Fault detection. It turns out that it's easier to detect faults if you have a deterministic model, because a deterministic model gives you a very clear definition of what a correct behavior is. And consequently, when you get incorrect behaviors, it's much easier to detect them. Simplicity. So a deterministic model has the property that there's one correct behavior for each input. So that can often make systems much easier to understand. Unsurprising behavior. Often having your system be boring is a good thing. And composability. If you're composing a system out of components, which we all do, if the component behavior is deterministic as a function of its inputs, and our composition semantics is also deterministic, then the composition behavior will also be a consequence of the composition and will be something you can determine from the composition. So that's an extremely valuable property. Now, when I talk about the value of determinism like this, a lot of people get very nervous, especially if they're people who have, say from the formal methods community, who have put their whole career into analyzing non-deterministic models. And by now they've gotten very defensive. And they're trying to find holes in my argument. There is nothing that I have said that undermines the value of non-deterministic models. Okay, non-deterministic models are also useful. They're just useful for different reasons and in different situations. So one way in which non-deterministic models are useful is that non-deterministic abstractions are often easier to understand. So this notion of abstraction and refinement is something that is really central to modeling in engineering enterprises, certainly, where an abstraction of a model may be a much smaller model. And if it's a sound abstraction, meaning that all of the behaviors of the model that it abstracts are also behaviors of the abstraction, then an analysis of the abstraction may yield information that is useful about the model that is being abstracted. So formal methods people use this kind of technique all the time. So this relationship between models of abstraction and refinement is a valuable one, and particularly when non-determinism is introduced into the models. Non-determinism is also useful when you have uncertainty about the world around you, or about the system, about the physics, about the physical environment. So you may need to model something that is not fully understood. So for example, if you have a cyber-physical system that has a human in the loop, it's probably not a reasonable expectation to construct a deterministic model of the human. Behaviors of humans are very difficult to model, and so you may be really much better off with a non-deterministic model. Uncertainty about your design is a rather different kind of uncertainty, where you would like to defer design decisions. So you might come up with a model of your system that has non-determinism in it because you're uncommitted at this point in the design process about what you're going to do about this particular part of the problem. Now, I'd like to zero in on these two kinds of uncertainty right here, because models are being used in two different ways here. When you're using non-determinism to handle uncertainty about the world, this is what I call a scientific model. When you're using non-determinism to model uncertainty about your design, I call this an engineering model. So let me give you a picture of this, okay? So you've got the world of physical things. So this is the thing in itself, to use Immanuel Kant's, the philosopher Immanuel Kant's term. You've got your physical artifact that lives in the physical world, your self-driving car as a three-dimensional object that actually drives on roads. That's a thing, okay? You can construct a scientific model of that, in which case the goal of the model is to describe the physical thing. And it's incumbent on the model to match the physical thing. But an engineering model is used in the reverse way. An engineering model is more like a specification of the physical thing. It's a model that we use to describe what we would like the physical thing to do. And then it's incumbent on the physical thing to match that model. And our goal in engineering is to make physical things that match those models. This is very much a parallel with abstraction and refinement. These are models that are working in relation in mirror image kinds of ways. I'd like to also point out, of course, that the relationship between models of abstraction and refinement are fundamentally mathematical models. So in an incredibly audacious single slide here, you see science, engineering, and mathematics all in one place. And this concept and this relationship between models and things is something that I talk quite a bit about in this book, Plato and the Nerd, which was published in 2017, just 4 years ago. So you've all heard George Box's famous quote, essentially all models are wrong, but some are useful. I realized when I was working on that book that George Box was talking about scientific models here, where it's incumbent on the model to match the physical thing. So the model is always wrong because it can never perfectly match the physical thing. So what's the mirror image for engineering? Well, essentially all system implementations are wrong, but some are useful. Given a model, every physical piece of silicon that you construct is wrong. It won't do the right thing if it overheats. It won't do the right thing as it ages. Eventually it will fail, okay? The physical implementation is wrong, but if it works well enough for a long enough time, it's useful. These are mirror images about models and things, and this plays very strongly into the concept of determinism. In the scientific view of determinism, which is enormously problematic, we're trying to construct deterministic models of the physical world, and we end up in all sorts of philosophical conundrums, like is causation really a property of the physical world? But in the engineering scenario, the problem is actually much simpler. We have a deterministic model of a system, synchronous digital design, for example, logic gates. And we would like to construct a physical thing that is reasonably faithful to that model. That's the challenge in engineering, and it's quite a different challenge from the challenge in science. So this concept of uncertainty and deferred design decisions, these are really two different kinds of uncertainty, and they're mirror images of one another. Now, there's other situations in which non-deterministic models are also valuable. So, for example, in the world of security, unpredictability can be good. You can also have engineering models where many behaviors are okay for the same input. So you want to be explicit about don't care conditions. So non-deterministic models can be useful for that. And then you might want surprising behavior. So for example, if you're trying to make conversational agents that interact with human beings, you don't really want them to be boring. So if you want unpredictable behavior and surprising behavior, non-determinism could be a useful tool. So let's zero in on cyber-physical systems. Cyber-physical systems from a modeling perspective, and especially a deterministic modeling perspective, are enormously challenging. I've already focused on why deterministic models of the physical world are so problematic. Deterministic models of the computational world, we use them all the time, but they're still problematic, right? We struggle with them, for example, with concurrent systems, where we all too frequently and all too easily give up on deterministic models, in my opinion, unnecessarily. Let's focus on one particular problem in cyber-physical systems, which is the role of time. So time in the physical world, you might model as Newtonian, or in certain circumstances as relativistic. In computational platforms, though, we don't really do that. In fact, our models of time tend to be pretty weak. And in the core abstractions of the computational world, time is just treated as sequences. That's certainly true in the case of imperative programs. And in the network fabric, when we talk about communication, we might talk about discrete events. So a big part of the problem in modeling cyber-physical systems is in reconciling these divergent views of time when you're really, of necessity, having to consider a holistic composition of these heterogeneous system components. So what is time? Well, in physics, it's hugely problematic. I mean, you can go back to Aristotle, where, Aristotle kind of modeled time as just change. Newton had what has been certainly one of the most successful models of time, but it turned out it was not very accurate, and relativistic time kind of undermined it. And one of the big debates in physics right now is whether time is actually continuous or discrete. If you look at what physicists say about this, you'll find that it's unresolved. So this book by Richard Muller about the physics of time, Muller gives a theory of time that requires, in order to be testable, he says that we're only going to be able to test this theory if we happen to have a couple of big black holes that collide somewhere near us and we can measure what they do. And Carlo Rovelli, in this book called The Order of Time, says the nature of time is perhaps the greatest remaining mystery. So how can we build systems based on something we don't understand? Well, is the goal of our model to accurately reflect the timing of the implementation? All too often in real-time systems, this is what I see people doing. They try to make the model accurately reflect the timing of the implementation. This is, for example, I'll tell you a little story. I got approached by a large industrial automation company. I won't mention which one, but they had simulation models for their industrial automation systems, and they were finding that they were not really accurate enough. And they had identified that the problem was that their simulation models weren't accurately enough predicting the timing behavior of the microcontrollers in the system. So they came to me saying, can you help me improve the accuracy of our modeling of the timing behavior of our microcontrollers? And I said, no, I can't help you with that. And moreover, I think it's the wrong thing to do. I think what you should do instead is figure out how to make your microcontrollers exhibit timing that corresponds with your models. In other words, the goal should be to have the implementation accurately reflect the timing of the model, not the other way around. If you approach the problem from this perspective, it's perfectly reasonable to think of deterministic timing. It's a very reasonable approach. If you put it, given a model with deterministic timing, your goal is to make the physical system match that timing. That's quite a different problem from given some physical system, try to figure out what its timing is. So what are the desirable properties that we want in some model of time? Well, let's just look at a few of those. So one of them is, in order to have a notion of the state of a system, you have to have a notion of a present. Separates the past and the future. The state of the system is what its state is at an instant in time. Unfortunately, none of the physical models are good at that. Okay, I guess the Newtonian model perhaps is the only one that has that, but it proves to be seriously problematic. In practice, it's problematic. It's not just in theory. Any distributed system has enormous difficulty with identifying a present and being able to have a well-defined notion of the state of the system. We need to have support for causality. So if one event causes another event, every observer should see those events in order. We need to have well-defined observers, and we need to have a notion of simultaneity. And all of these are problematic in physics, really useful in models. So if you approach the problem as an engineering modeling problem and forget about the physics of the model, then the question is, well, what should the timing model be? Well, this leads to the latest manifestation of my obsession with determinism, which is this Lingua franca project that Albert mentioned briefly in his very kind introduction. And this is a collaborative project. Here is a screenshot from our conference call just yesterday that shows a few of the people who are the part of the core design. And you can see, in fact, in some ways, this project, I think, in some ways actually benefited from the pandemic because it's a much more globally distributed project. We have participants in Germany and Korea and across the US that are working on this project. And I'm really enjoying this collaboration with these incredibly talented people. But I'd like to give you a sense of what this language is about. First of all, it's a polyglot language. So it's not like so many languages out there. It's not trying to get you to give up on your favorite programming language. You like programming in Python? Fine, program in Python. You like programming in C++? Fine, program in C++. Lingua franca creates wrappers around code that you write in your favorite language. Currently, the languages that are supported are C, C++, Python, and TypeScript, which is a dialect of JavaScript. And the way that, here's a couple of snippets from the language. So here's a chunk of C code inside of a reaction. And this reaction happens to be triggered by a shutdown of the program. And this triggering of a reaction is something that the language framework, the Lingua franca framework, makes deterministic. So every component in the system will have any shutdown reactions that it has will be invoked logically simultaneously. And the framework guarantees that. And it defines logical simultaneity in a very clean way by restricting what observers can see and ensuring that any observer that sees that one of these shutdown functions has been invoked will see that all of the shutdown functions have been invoked. So this control of information flow is a key part of how you get a deterministic model. There's also a very lovely interactive visualization associated with this language, mostly designed by Alexander Schultz Rosengarten of the University of Kiel in northern Germany. And it's an enormously valuable tool for visualizing what's going on in these programs. So the language makes a logical notion of time a first-class member of the program. So for example, you can define timers that have periodic behavior, and every timer throughout the system with the same offset and same period will have reactions invoked logically simultaneously. And the framework guarantees that even in a distributed system. And that notion of logical simultaneity is a semantic property of the language. You can also have variations in timing that are under program control, but still yield deterministic behavior. And these use a mechanism that in the language are called logical actions, where you can compute time delays and then insert them into your program in a deterministic way. And in execution of the program that I just showed, the way that it works is there's a command line compiler. There's also the IDE that the screenshots that I showed you from the IDE, the visualization is in the IDE, but there's a language, there's a command line compiler. If the target language is C, the command line compiler will produce a standalone C program and then compile it using GCC. And then you can execute that program. And the program has both a logical notion of time and a physical notion of time that coexist within the system. And the logical notion of time has a deterministic semantics. And the physical notion of time is aligned with the logical notion of time on a best effort basis using standard real-time systems techniques such as earliest deadline first scheduling and the like. You can also have asynchronous external events that come into the system. They get assigned timestamps using the physical clock of a system, and the mechanism in the language is called a physical action. Once a physical action has been assigned a timestamp, the way the program reacts to it is deterministic. You can specify deadlines, which are used for guiding scheduling, but they're also used for fault handling. So in particular, I can specify a fault handler that is a piece of code that will be invoked instead of a regular reaction if a deadline is violated. And so being able to specify fault handlers within the program is a way of introducing a controlled form of non-determinism. Okay, this will actually make the program non-deterministic because now the behavior of the program will depend on execution times, which are not specified within the program. And consequently, you get a controlled form of non-determinism where the program may, in fact, exhibit non-deterministic behavior where a deadline handler is invoked instead of a regular reaction. But now within the context of the program, if you have good analysis tools, for example, worst case execution time tools, you might be able to prove that the deadline handler never gets invoked on some particular physical realization. Lingua franca programs can also be distributed across networks. A lot of the infrastructure for doing that was developed by Sarush Bateni, a very talented graduate student from the University of Texas at Dallas that we've been collaborating with for several years now. And so you can map components in the system onto different hosts, and the code generator automatically synthesizes the communication between them such that the deterministic semantics is preserved even across the network. And I'd like to contrast that with the way that things are often done. In particular, sorry, I'm doing this a little bit out of order. So let me just first point out that we have two different mechanisms for handling the coordination across a distributed system. There's a centralized coordinator, which enforces deterministic semantics irrespective of network delays. Okay, if you think about it, that can be problematic because it means that if your network gets partitioned, you sever the network, then progress must stop, right? Because the deterministic semantics can't be enforced until your network gets repaired. Okay, so that might be undesirable for some applications. So the decentralized coordinator does kind of a mirror image behavior. It enforces forward progress. It guarantees that there will be forward progress in components of the system, but delivers deterministic semantics only under certain assumptions about the network. So for example, if you have bounds on network delay, then you will get deterministic semantics. But if your network delays become unbounded or exceed your assumed bounds, then you get non-deterministic semantics. But again, we have a way of introducing a controlled form of that where you define fault handlers that detect violations of this deterministic semantics. So in particular, these are the assumptions. Deadlines will be met. If deadlines are met, then a non-distributed lingua franca program will always be deterministic. Okay, if the deadlines are met, it will be deterministic. Even a multi-threaded execution of it will be deterministic. You can ensure that deadlines are met using worst case execution time analysis and doing schedulability analysis on the system. In a federated execution, we also need to assume that deadlines are met, but also that network latency is bounded, and if you use decentralized coordination, that clock synchronization error is bounded too. If these assumptions are met, you get deterministic semantics. Otherwise, you get non-deterministic semantics, but with fault handlers that can be invoked when the non-determinism kicks in. So I'd like to contrast this with the most popular techniques that are used today for distributed systems. So ROS, used in robotics, which has a publish and subscribe communication fabric. The communication fabric is fundamentally non-deterministic. And as a consequence, ROS programs sometimes exhibit quite surprising behavior. And one of the more disturbing parts about ROS programs is that the non-determinism is sometimes really quite rare, which means that testing doesn't reveal the flaw because it's unlikely to occur in testing. But there's an underlying non-determinism that is likely to manifest in the physical world. So you can find similar flaws in actor-based methodologies, in shared memory techniques, and in service-oriented architectures. And these are very commonly used, but in lingua franca, we're trying to replace all of those with more deterministic mechanisms. So this, you might be nervous, right? Because I've said lingua franca programs can admit non-determinism. If deadlines get violated, you'll get non-deterministic behavior. If you've assumed bounded network latency and that assumption is violated, you get non-determinism. This drives at the root of the difference between scientific models and engineering models. So in science, the value of a model lies in how well its behavior matches that of a physical system. In engineering, the value of the physical system lies in how well its behavior matches that of the model. Okay? If your physical realization fails to deliver the execution time bounds that you expected, it's the physical system that is at fault. Okay? If it fails to do this because of some problem with the clocking, some problem with temperature, some cause like that, it's the physical system that's at fault, not the model. And the lingua franca framework gives you a way to detect these fault conditions. So another way to think about this is a scientist asks, can I make a model for this thing? Whereas an engineer asks, can I make a thing for this model? And a lingua franca program is an engineering model, and its value depends on the ability of the physical system to match the model. Now, one final point that I'd like to make is that determinism, of course, like anything else, has its limits. I've already talked about the limits imposed by chaos and uncertainty. I'd like to talk about one really fundamental limit, which is incompleteness. So in 2016, I published a paper in the very first ACM Transactions on Cyber-Physical Systems, Volume 1, Number 1. I love the fact that this was in the very first issue. It's called Fundamental Limits. And in this paper, I prove that any set of deterministic models that's rich enough to encompass Newton's laws and also has discrete transitions, that any such set is incomplete. And to give you a sense of how I prove that is I consider a scenario that you can model using Newton's laws that involves collisions of spherical objects. And in particular, collisions where there's a possibility of the collisions being simultaneous. So you have two billiard balls converging on a single billiard ball, and they might collide at slightly different times, but in the limit, you might get to the point where you actually have simultaneous collisions. So I show that you can construct a Cauchy sequence of deterministic models. So it's a Cauchy sequence in the metric space sense, which means that the models are getting closer and closer to one another in a metric space. Okay, and the models form a sequence where the time between collisions approaches zero. Each model in the sequence is deterministic, but there is no deterministic model that is the limit of the sequence. And the fact that there is no such model follows from Newton's laws. Okay, so I show that in the paper, which means that any set of deterministic models that's rich enough is going to have to admit non-deterministic models. So you might say, well, if non-determinism is unavoidable, why don't we just embrace it? Let's just give up on deterministic models and we'll just use, let's just use publish and subscribe. The world is unpredictable anyway. We're going to have to design our systems to handle non-determinism. I think that's not the right attitude. Death is also unavoidable, but we all try to avoid it. So the argument that it's unavoidable and therefore we should embrace it just simply doesn't follow. So for cyber-physical systems, the question is not whether deterministic models can describe the behavior of cyber-physical systems with high fidelity. That's the wrong question. The right question is whether we can build cyber-physical systems whose behavior matches that of a deterministic model with high probability. That's a much better question. I know how to answer that question, in fact. And in fact, much of engineering in the world of computing has been all about answering that question for the last 50 years or so. Determinism, wait a minute, what about robustness, fault tolerance? Well, actually deterministic models enable fault tolerant design because they make it much clearer what it means to have a fault. The ability in Lingua franca programs to explicitly put in fault handlers, which are violations of your assumptions. The fault handlers get triggered when your assumptions are violated. And that ability to put in these fault handlers is, I think, a unique feature of that language. So in conclusion, you can find a lot more about this in these various references. And with that, I would like to end and open up for questions. Thank you very much.
Thank you, Edward. Thank you. A very insightful, very understanding talk. So let's open the floor for any questions or comments from the audience. And I see a hand from Jixing. Jixing, please go ahead.
Oh, thanks, Professor Lee. Very inspiring and philosophical talk. I like to. There's currently there's this endeavor in industry that's heavily using. Hello, yeah, in industry that is using computer vision and to assist driving. So according to your direction,
unfortunately your audio is very choppy, and I'm also trying to figure out how. For some reason, Microsoft's software hides the button that turns off screen sharing.
Okay, let me try to use chat box.
Yes.
It's
very choppy also from here. I guess you are in Hong Kong, so there is maybe a lot of non-determinism or determinism traveling.
Let me use
chat a little bit and yeah.
Okay, I give up on finding the button that stops the screen sharing. So sorry about that. You just have to look at my rather boring screen here. It's just not there.
This is my question in the chat box.
Okay, I'm not sure how to get the chat box either. These controls are really ridiculous.
Can Albert read?
Carlos, are you there? Can you help? So the chat should be next to the to the icon of people. So
yeah, the thing is, a screen is another window, so it's not that window. There should be another window. If you go to in the menu where it says window,
Window.
yes,
Window.
then you see here. You should have other windows where. No, it should be another one.
Okay. Stop presenting. Yeah. Boy,
Okay.
that's a really terrible user interface. Okay.
Okay.
Um,
So my question, I have typed it in the chat box. So basically, do you think the current industry in
okay, I got it. So do I think it's wrong in industry to use computer vision and AI to do autopilot? That's a wonderful question, and I actually address that question in some detail in my coevolution book. I think that a lot of the newer AI and machine learning based techniques are more properly viewed as part of your sensing system and not as part of your control system. And control system engineers have always had to deal with imperfect sensors. That's an intrinsic part of doing control system design. And so if you think of the perception system in a self-driving car that's using vision, for example, as part of your sensing system, then you use standard techniques that control system engineers have always used to deal with imperfections in your sensing system. So I don't think it's wrong at all to use these things. I think when you're using the AIs for higher level functions, so when you use them directly in the control loop, for example, that can still be okay as long as there are ways to formally bound the behavior, right? If you can provide safety envelopes around the behavior, then, and you can detect deviations from those safety envelopes, then I think that is also potentially very legitimate use of those kinds of techniques. But yeah, so very good question.
Thank you very
I
much.
see another question from Tanimoto Tadaki. Using uncountable infinity, we can draw mathematically correct conclusions that make us feel inconsistent. Does that mean it appears in the debate about determinacy? That's a pretty deep question. And I think that, you know, one of the, I talked a little bit in my talk about chaos, okay, and chaos actually is particularly bad in continuous systems. It also can be exhibited in discrete behaviors such as cellular automata, but it's actually you know, much worse in continuous systems where you deal with uncountable infinities. So I think that your concern about determinacy and its relationship with this mathematical concept is a very valid one, right? But again, I would like to emphasize that if we treat determinacy as a property of models, not as a property of the physical system, then the problem becomes less bad, okay? But so many people assume that Newton's laws give a deterministic model of the physical world. In my recent paper on determinism in the Transactions on Embedded Computing Systems, I talk at some depth about a demonstration that that's actually not the case, that Newton's laws actually admit non-deterministic behaviors. And it turns out that there's been a very, very rich debate around a particular problem scenario that was originally proposed by the philosopher John Norton. And it centers around these mathematical continuums, you know, whether this is really a property of Newton's laws or not. So that debate, I think, drives to the heart of the difficulty of this question. So I don't have a simple answer for that question, but it's a wonderful question.
Thank you. So, other questions? If there's none, let me ask maybe a simple question or a naive question to Edward. And I think earlier in the presentations, you mentioned that deterministic model allow or makes it easier for fault detection, right? So my question is, would deterministic model make it easier to detect faults and also to do fault recovery in hardware? So let's say there are hardware faults like bit flips, due to radiation or other elements of space. So would deterministic models make it easier to detect faults and also recover from these faults, whether done in the hardware or at the software layer or in some kind of co-design, techniques?
Yeah, let me give a really simple example that I think really drives home how deterministic models can make fault detection so much easier. Think of computer memories. So in particular, let's think of DRAM, right? So what is DRAM? It's a bunch of electrons in a bucket, right? That are holding a charge for some period of time. In any reasonable physical model of what's going on there is probably going to admit non-deterministic behaviors, right? But we have a very simple deterministic model of that memory, which is that the bits that you write into it are the same as the bits that you read out of it. We also have a deterministic model for constructing cyclic redundancy checks, okay? Which is, you add another bit that will tell you whether the bits that you've just read out, if there's a single bit flip that occurs, you can detect it, okay? So here you've used two deterministic models, a deterministic model for the memory and a deterministic model for the CRC computation to detect violations of the first deterministic model, okay? It won't detect all violations. If you get 2 bit flips, your CRC will fail to detect that, right? But it'll detect 1. So that's a very simple example of where deterministic models actually help you with. If on the other hand, you directly embrace the physics and tried to say, well, okay, a memory is a bucket of electrons. Let me count the electrons and see if there's really enough of them there, right? That would be a very difficult way to detect faults.
Okay, thank you, Edward. Yeah. All right, so are there any other comments before we close the session? Going once, going twice. All right, so done. Let me see, look at the chat one more time. Thank you. Okay, thank you for the presentation. Excellent. So thank you very much to Professor Edward Lee for the excellent talk, really inspired conversation. Thank you very much. And so we'll see you again tomorrow here, for another day of exciting program. And stay safe and see you tomorrow. Thank you again.